Okay, thanks. Well, thanks everyone for joining us today for the AWS Community Day in Amsterdam. It's really a pleasure to be here and talk to you about Amazon EventBridge. My name is James Beswick, and I'm a serverless developer advocate. And before I was a DA, I was a software developer for many years and also a product manager for a very long time. I've been a self-confessed serverless geek for quite a long time and spent many years building applications entirely from serverless. The most important thing on this slide is my email address and my Twitter handle. So if you have any questions at all about serverless, Lambda, EventBridge, or anything else after today, feel free to reach out to me anytime, and I'll do my best to help. So we're going to cover three things today in 20 minutes. First, I'll talk about the challenges of using microservices as we've moved from monoliths. Next, I'll explain how an event bus like EventBridge can help solve some of these issues. And finally, I'll take a look at how the service works and how it fits into some of the concepts I cover in the first section. I'll give you some additional resources too, so you can explore this service after the session. So let's talk a little bit about some of the challenges associated with building these kinds of distributed systems. The first thing I want to talk about today is coupling. One of the big benefits that's often cited with microservices is that often these services are loosely coupled or decoupled. But it's important to recognize that anytime you have two systems talking to each other, there's some degree of coupling happening there. And you need to understand the long-term ramifications of that for your system. This is a standard synchronous API. I'm sure we've all written plenty of these. And in this example, a client comes in and posts an order to an order service, which turns around and posts another request to an invoice service, which then does some work, and then it returns a 201, maybe an invoice number as well, and that gets returned to the client. And so you take a very simple example like this, and you just have two services, and there's no monolith at this stage. It's actually just very simply two separate systems. But what happens when we add more and more services that integrate with the order service? What starts to happen is the order service gets more responsibilities and more complexity. And the order service has to understand things like retry semantics for each one of the services, and maybe bundle an SDK for each one. Even if downstream publishers have an API, it becomes on the order service to integrate the API into this overall system. And if there are any backwards incompatible changes to the APIs, again, the order service team is on the hook to update this. So long term, there are more and more services out there that need data from the order service. And in this model, the teams end up being blocked by the order service team to implement these changes. And they cannot operate independently as they once could. So it creates unnecessary friction in the process due to the integration cost of hooking these services together, and that slows down the development process. So when you get to this stage, the decoupling has gone, and now we're back to working with a monolith. And it's a really common pattern, systems starting off in a decoupled way and trending back towards being monolithic. So what can we do about this? Here's a second issue. As APIs develop into complex workflows, it can be difficult to make sure that each service has the right state. So here's the same e-commerce application with some additional downstream services. I've added fulfillment and shipping. In the happy path, everything works as expected. The order service triggers the invoicing, payment, and forecasting services. And then once the payment clears, that triggers fulfillment. Then once that happens, that triggers shipping. But what happens if the fulfillment service cannot find a product because it's not on the shelf and they're out of stock? So now the fulfillment service has to tell the order service that it needs a modification. Maybe it then has to send a message to reverse a payment or issue a refund or a partial credit. And the shipping service may have already been told, so they have to send a message back to the invoice service as well. And then the forecasting service may not accept these kind of modifications, so it could just be broken until somebody makes a manual change. So this is just the remediation path for one possible thing that could go wrong in just one of the services. Now here's another one that happens fairly frequently too. Imagine your team works on the payment service, but you weren't told that another service, a reward service in this case, was added. So what happens now when the fulfillment service errors as before? Maybe the fulfillment service orchestrates all these other services as we saw, but the reward service team never finds out. And the end result is that a cancelled order ends up with a reward for a customer, which definitely wasn't the intention. Also, what happens if the reward service changes vendors, maybe adds another API? Does your team know about this, with an old service pinging a new one to keep it in sync? So ultimately, it's really hard to keep these sorts of systems orchestrated and in sync because of the complexity when you start to add more and more services. Here's one more issue. Let's talk about availability in these systems. So back to our ordering system where the team is managing payments. There are a number of potential problems here. The first is performance mismatch. It takes longer to process payments than it does to send invoices. So in busy periods, your slower performance is holding up the order service and the customer is experiencing delays. In synchronous APIs, putting a fast service in front of a slow service can tend to lead to a lot of problems. The second issue are outages. So if the payment system goes down, the order service also goes down. So the availability numbers for the total service are worse because these systems are interdependent. And the downstream failure appears as a total failure for the end user. So how can events help with these three different challenges? Well, first, what is an event? Well, in its simplest terms, an event is simply a signal that a system state has changed. It's often represented as a JSON object, and it contains some set of facts about the event or the change itself, and potentially the new state of the system. Events typically have certain attributes, so they may be facts, for example, and they're immutable, they don't change. They're observable, and they're temporal. The time of the event really matters to the system. And we're really interested in the fact that they're observable instead of being directed. So what does this mean? Well, in a command model, commands are explicitly issued to a specific recipient. So in this example, the person on the left says to the person on the right, please create me an invoice. And this is a directed command. In an observable system, the person on the left says custom X just ordered a widget. And with 4 people listening, one decides to add that to the sales report, another decides to send an invoice, and 2 to take no action at all, even though they hear the event. And this is a subtle difference, but a really important one, that event producers don't need to know about who's listening to the event. And this keeps them very simple and allows other services to consume events without needing any upstream changes. So how do we actually implement this? Well, how do we pass information from this order service to all of these services downstream without actually calling them directly? Well, for that, we need an event bus. And this provides an endpoint where an event producer can send events. The router manages directing and filtering those events to the appropriate downstream consumers. And consumers can get the events they care about, and they can do this reliably while the producers remain completely decoupled. So our architecture now looks like this. The order service sends events to the bus, which is configured with rules which determine which downstream systems get the events. Some targets will only care about certain events, others will want all the events. But either way, the router now takes on the complexity of ensuring that these events get propagated appropriately to each downstream service. So back in our example with an event bus decoupling the architecture, it actually looks very similar. But if the fulfillment service raises an error as before, they simply raise an error event. And this is caught by other services that are listening, and they can then take action accordingly. Now, in the other problem example I talked about, where a reward service is added, for another team to consume some of the order service's events, they just need to add a new rule to the bus. There's no need to wait on the order service team to make an integration or any kind of update for them. So these service teams can now act more independently and move faster. So as your applications expand to include other systems beyond your immediate control, you need to pass information to and from those services. Since you don't own the code, it can actually be hard to get that information out of those systems. And we've got a couple of different ways traditionally to do this. The first option is polling. So in this case, you might have something like a Lambda function that's triggered every minute to query a service, and that then generates events based upon that information. Now, in this case, this is generally okay if the payloads are not too large, But it tends to be a last resort option because there's an unnecessary lag between data becoming available in the service and you knowing about it, and it creates unnecessary load on the API due to the number of empty calls with no information coming back. You also have to manage this polling service. The second option is webhooks. This is a much better option generally, but only if your SaaS provider supports the idea. You provide the SaaS provider with an HTTP endpoint, and they post or get information as it becomes available. You can use a custom authorizer to validate the calls, and now the data you're getting is much closer to real time. But there are some problems with webhooks that people commonly don't think about. If your service goes down for any reason, you may lose information. It's possible the SaaS provider doesn't have any retry logic to call you again. These endpoints are internet facing, so you have to secure those and write custom authorizers. Often the security model here can use static secrets like API keys, which isn't really the best approach. And you have to manage this API, and of course you have to manage scale. If the event provider sends you a lot of events at once, you have to make sure that your API endpoint can scale up and accept all of that traffic. So can we do better than this? Well, within AWS, we have a fairly new serverless event bus service, and it's called Amazon EventBridge. This was announced at the AWS Summit last year in New York. So this is a serverless event bus service that makes events first-class citizens across your entire workload. It can help you ingest and route events from SaaS applications, AWS services, and your own systems. It's not actually a completely brand new service. It evolved from CloudWatch events. So it already processes trillions of events every month. Some of the notable features of EventBridge include the fact that it's serverless, so there's no infrastructure for you to manage or provision. Scaling is handled automatically, and you only pay for what you use. It was launched with a range of native integrations with different SaaS providers, and there's many more coming. The traffic that comes into EventBridge travels internally on the AWS infrastructure instead of on the public internet, which can make things more secure. There's also no charge for events that are sourced from AWS services, and when you put events onto the bus, it costs $1 per million events. So how does it work? Well, on the left-hand side, it all starts with an event source. This can be any one of 95 AWS services, or your Lambda functions and applications, or SaaS applications. For SaaS application integration, there's a special resource that appears called a partner event source. And then there's event buses. So everybody has a default event bus in your AWS account in each region. It's always there. You can create your own custom event buses for your applications. And then there are buses dedicated to ingesting partner events. And then there are rules. So rules can basically use complex rule handling to figure out what's in the event and where then it should be routed to. So to give you an example of this, here's an example event of what happens when a ticket is created and it has an ID and it comes from a certain department. A rule might look like this. So a rule is just JSON, just like the event, and it might match on a source, looking for partner example.com 123. So in this case, the rule would match the event. You can also in rules specify multiple values. So if you wanted to match on multiple departments in this case, you could match on billing and fulfillment by using an array in your rule. Again, this would match. Well, here's an example of one that doesn't match because the rule is looking for a detail type of ticket resolved, but the example event shows a created ticket. So once you have your rules, that then routes the events to targets. And you can associate multiple targets with each rule to send events further on. So targets allow you to do things like invoke a Lambda function, or put a record on a Kinesis data stream or Firehose, or start the execution of an AWS step functions workflow, or start a task with ECS or Fargate. So that's the concept and the idea behind EventBridge, but let's take a look at how the code actually works. So to keep this simple, let's go back to the original example where we have an order service and an invoice service. We're going to put an event bus between them so it looks like this. Now let's put some code in there. So on the left-hand side, the order service, now what it does is it creates that event object, which is JSON, shown here. And this example shows that it has a source of demo.orders, and the detail type is a new order. The final line at the bottom, eventbridge.putEvents, is the method called to put the event on the bus. So you can do that with one line of code. When that code returns, that means that the event has been durably stored on the bus. On the right-hand side, you'll see the invoice service actually doesn't contain very much code at all, because it's actually agnostic about where the event comes from. It simply receives the event and goes about its work as it would have done before. So the important thing here is the rule. The rule defines what happens. So this example is written in CloudFormation. For serverless users, you can also use SAM. The key things to notice here are that it's matching on an event pattern where the source equals demo.orders and the state equals created. It then defines a target of the Lambda function, the invoice service function in this case. So if you look back at this, the order service is generating the event of a new order, and then on the right-hand side, the invoice service is ready to pick up the event when it's routed there by the rule. So earlier I talked about the difficulty of adding new services in orchestrating workflows. So how do you handle adding a reward service with an event bus? It's actually as simple as adding another rule. And that's very similar to the last example, but the target is different. So by adding this rule, the same event pattern will now trigger a new target, in this case, reward service. And if we wanted the reward service to be triggered by a different event, we simply change the event pattern. So with events, it really is very simple. Now, recently, the EventBridge schema registry was launched, and this allows you to discover, create, and manage open API schemas for events that are flowing through your workflow with EventBridge. You can find schemas for existing AWS services and create and upload custom schemas or generate a schema based on events for the event bus. For all schemas in EventBridge, you can generate and download code bindings into your IDE, and that will help you quickly create a code to help you build new applications based upon those events. So in this talk, we covered a few of the common challenges of managing complex microservices, both in private applications and across third-party systems. Decoupling with APIs and webhook mechanisms tends to lock you into a more rigid, more complex and monolithic state, even in separate services. An event bus can help you keep these services decoupled, even as your systems become more complex, and with new versions of those services. We saw how the happy path works well, but handling error states can be really difficult to orchestrate. Event buses can help you manage those errors across complex workflows and help ensure that your service teams remain decoupled, only listening to the events that they care about and being responsible for the events that they're creating. In synchronous APIs, the availability of the entire system can be impacted by the failure of any single service. So moving towards an asynchronous infrastructure based around events allows you to create more resilience in your architecture, and with the right architecture design, can improve availability. For third-party integrations, I showed how webhooks are better than polling, but they come with their own challenges. So EventBridge offers SaaS integrations with a growing number of partners that can treat new data in these systems as events. So for a collection of code examples, blogs, and videos showing how to use an event bus, go to the link on the screen, s12d.com/eventbridge. I think that events can really make complex architectures much more resilient and easier to maintain. So thanks very much for listening to this. My name is James Beswick. I'm a DA with AWS Serverless. I'd be really happy to answer any questions that you might have.
Oh, thank you so much, James. It was a very nice presentation about the EventBridge.
Thank you.
So I see that we don't have a question from the audience, but myself, as I promised at the beginning, I have some question from you. So I'm very curious about all of these event services. So when I can make sure and how I can decide which service I will use for the event. For example, let's say I will use SQS like queue. I will use SNS for a topic, or I will use EventBridge, and when I am going to use EventBridge.
Yeah, great question. I hear this one very frequently. So there are three services. You have SQS, SNS, and EventBridge. SQS handles queues, SNS is a pub subservice, and EventBridge is an event bus. And in some respects, they have similar overlapping functionality, but actually, once you start looking at what they can provide, they're all a bit different. So the most obvious difference is that SQS, being a queue, that's functionality that's not available in either SNS or EventBridge. SNS also has a different range of targets, including things like mobile addresses or HTTP endpoints, and can deal with up to millions of subscribers, whereas EventBridge tends to only deal with smaller numbers of targets. But the really exciting thing here is you can combine these services to solve different problems. And it's something I recently blogged about on the Compute blog. If you have a look online, I've put some examples out there. But really interestingly, you can take SQS and combine it with EventBridge. And that's a really simple, low-code way to add resilience to your workflows. So if something goes down or there's an outage somewhere in your system, the messages are then stored in SQS. So even though these systems are all part of the messaging architecture that we provide and do have some similarities, they have very different features in terms of how they can be implemented in your workload.
Oh, thank you so much. They're really awesome and useful answer. And I have another question as well. Which services can send the events to EventBridge? So there are a couple of services features that can send all the events.
Yes, so the goal really of EventBridge is to make it so events become first-class citizens within your infrastructure. And so pretty much anything within AWS can generate an event of some sort. Now, some of these services have native integrations with EventBridge and can directly send events to the bus. Ones that don't have that native integration, you can still ingest the events via CloudTrail. So for example, if you want to pick up events from S3, you can use CloudTrail to pick up those events directly into your bus. But it goes beyond just what's available within AWS. So if you look at what's provided with SaaS providers, people like Datadog or PagerDuty or Auth0, they can also generate events that appear directly in your AWS account on these partner buses. And of course, you can generate events from your own applications, whether that's Lambda functions, EC2-based applications, or whatever you might have. So really anything within AWS has the ability to create an event that can then be put onto the event bus.
Thank you so much, James. Thank you so much. It was really nice presentation about EventBridge.
Great.
Definitely, I'm going to learn more about EventBridge. I'm going to do some tests to understand much better. So thank you, and see you in the next session.
Yeah, thanks very much. If anybody has any questions, please feel free to reach out to me. My contact details are on the screen. And also take a look at serverlessland.com. We've put a lot of different examples, blogs, and code that can help you discover more about AWS serverless. Otherwise, thanks very much for inviting me. I've had a great time. I hope everyone enjoys the rest of the day here at AWS Community Days Amsterdam.
Thank you.